Okay, so hello there. My name is Vilina Helena Sapan, and I'm from IF46 INT class. And as usual, I'm going to explain about mathematical problems in calculus. And now I'm going to explain about the convergence test for series. Okay, the first test that I'm going to explain is the integral test. So we have this problem. Okay, so we want to know if this series is convergent or divergent. And we're gonna evaluate it by using the integral test. So, okay, so this function 2 over 3n plus 5 is already continuous, positive, and decreasing. So the next step is we have to evaluate the integral. So we need to look at the integral from 1 to infinity of 2 over 3n plus 5. And this is an improper integral. So by definition, it is the limit as b goes to infinity of the integral from 1 to b of 2 over 3x plus 5 dx. Okay, so next, let's pull out the 2. Next, after we integrate this, the 1 over 3x plus 5, it will be equal to the natural logarithm of 3x plus 5, and we'll evaluate it between b and 1. So next, we'll substitute the bounds of integration. Okay, and then simplify it a little bit more. Okay, because this b goes to infinity, that means this natural logarithm of 3b plus 5 will also go to infinity. And that means the result is infinity. And this concludes that this integral is divergent. And that means the series will also be divergent. Okay, we can see it by this definition. So if the integral is divergent, then the series is divergent. Okay, next I'm going to explain about the p-series test or hyperharmonic test. Okay, this is the theorem, and we have, okay, so we need to find its sigma form, right? So we can write down this. Okay, the sigma form with n starts with 1. So the numerator pattern is just 1. And then we have to determine the denominator pattern. So we got this 4 from 2 squared, right? And this 9 from 3 squared, and this 16 from 4 squared, and 25 from 5 squared. So we can just write down the cube root of n to the power of 2. Yeah. So we just need to change the denominator. So we need to change this cube root form into the fraction form. So we'll get 1 over n to the power of 2/3. Okay. And then we get the p. The p is equal to 2/3. And that's why the p is less than 1. And if p is less than 1, then it means the series is divergent. Okay, so next is the direct comparison test. you can see here that I put the theorem for the direct comparison test on the left side, and on the right side I put the theorem for the p-series test, because that theorem will be useful for our calculation later. So we have, so in this direct comparison test, we need to find if this series is convergent or divergent by comparing the original series with more familiar series. So we can just pick, okay, I'm going to use 1 over 3n squared. Okay, so why did I choose this series to be compared to the original series? It's because of these requirements. But before that, I'm going to call the original series function by an and the comparison series function by bn. Okay, so as you can see here, that the requirements is an must be less than bn. Okay, so you can see here that the denominator of an, which is 3n squared plus 2, is larger than the denominator of bn. When you divide by a larger number, you will get a smaller ratio. So we can conclude that an is less than bn. Okay. Then after we fulfill the requirements, we need to know if bn is convergent or not. So we can use the p-series test. So we have p is equal to 2 here, and p is larger than 1. That means it is convergent. So if bn is convergent, then an is convergent as well. Okay, next I'm going to explain about the limit comparison test. Okay, this is the theorem. And on the right side, again, I put the p-series test theorem because it will also be useful for our calculation later. So we have, okay. So we're gonna determine if the series is convergent or divergent. So first, we have to distribute the denominator. Okay, so next we have to find the L. So according to the definition, L is equal to limit as n goes to infinity of a sub n over b sub n. So I'm going to call the original series as as of n. And for the b sub n, I will pick I will pick 1 over n to the fourth. Okay. Okay. Next, I'm going to do this calculation of L. So limit as n goes to infinity. Okay. So I'm going to execute flipping and multiplying. And we'll get n to the fourth over n to the fourth plus 4 times n squared. Okay. Okay. Next, we need to divide the numerator and the denominator by the highest degree. We'll get It means L is equal to 1. So by definition, if L is equal to 1, then it means L is larger than 0. So that means the AN and BN can be both convergent or both divergent. So that's why we need to find out if BN is convergent or divergent. So we can use the P series test. We have P equals 4 here, and P is larger than 1. That means series of Bn is convergent. And that makes the series of An is convergent as well. Okay, so that is the end of my explanation. I hope you can understand my explanation well. Thank you for listening, and thank you for your attention. Bye.